Hello everyone, welcome to today's presentation on concrete slab modeling, analysis, and design in S-frame. We'll introduce the process and concept behind slab design in S-frame, including finite element modeling of our slab. We'll look at the analysis and design of our slab using S-frame's finite element solver. I'll show you some ways to refine your model for more accurate results and how you can report those results to others using built-in tools. And once we're done, we'll wrap things up and answer any questions that you might have. So S-frame's finite element solver can help us to design our slab. But why should we use S-frame? Well, for various reasons. Our slabs are not always regular in practice. This can complicate the code checking process, which would really be quite hard to do by hand. And that's normally often how that's done. S-frame's finite element solver is an accurate and sophisticated way of analyzing our slab. And while the finite element analysis in S-frame is very capable, it is important that you, the engineer, be vigilant of the results and understand how they are calculated, and you understand what exactly S-frame is taught you. So hopefully we'll be able to clear up some of that confusion today. Now, in order to get accurate design data for our analysis, it's important that the modeling process be done correctly. S-frame has industry-leading finite element modeling capabilities that can make this process a lot easier for you, regardless of the complexity of your structure. We'll look at an example of a single floor plan that isn't completely symmetric. Using S-frame, the flexural steel reinforcement requirements of our reinforced concrete slab can then be determined as well. And we'll also look at how integrated concrete design can fit into that equation. So we'll use the following structure to show how slab design can be done in S-frame. Finite element modeling is suitable for irregular layouts. Slabs with openings, for instance, like we have here, are a good candidate of that. We can always make simplifications as necessary, but that's not always necessary, so we can really leave that up to the engineer to do that. S-frame should be able to model pretty much any slab you throw at it. With our finite element model, we can use Wood-Armor equations to ensure the capacity of the slab is not exceeded in flexure by loading, while minimizing the total amount of reinforcement required. So here I have the start of my model. This is again representing that same model I just showed you. I did make a few simplifications. For instance, there's a few areas where I had just a thin strip of concrete that would have been bordering this whole panel here. I just chose to leave that thin strip of concrete out, but we could have certainly left it in. It just comes down to preference. You can see here, if I look at my geometry window, we have some concrete columns already defined. We also have a panel, a couple panels actually, to represent our slab. So we have a shell mix mesh panel to represent the actual meshable components of our slab, and then we have a few hole panels as well. I'll just show you a few details on these. So we can see that it's 300 millimeter thick concrete. You can look at the mesh density of 25. And we can see a quad weight as well of 90%. Now, if you're not familiar with these, it's not completely crucial for the understanding of this whole concept. There's more information in the help system. As well, we have a lot of great details within our finite element analysis online training course. But we can see here that these yellow panels that we see, those are going to represent hole panels. So we're not going to have any mesh within those locations. We just have to tell S-frame where we don't want to have that mesh. I also want to verify that I'm using the correct material properties. So you can see I have two different concrete material properties, slab concrete and column concrete. And you can see they're assigned probably as how I want them to be. So the next step is to go ahead and mesh our panel. So I'm going to click on Mesh Panel Elements of type membrane, plate, or shell. And you can see here that S-frame has created this meshable panel, it's discretized it, and created these meshed elements. So I have shell elements created based on this, the parameters I set for my panel. I'm going to accept this. It gives me the option here to either remesh with different parameters or continue forward with this particular mesh. So I'm going to click yes to move forward. And we can see here if we zoom in, that the tips of all our columns are integrated within our mesh. We don't have to worry about connecting those to the elements. That's already done for us in the meshing algorithms. And our hole panels as well are being created, and there's no mesh going within those hole panels. So we have this pretty well taken care of with the automatic meshing. Now I'm going to work on my loading next. I have one load case. It's an empty load case right now. But I'm actually going to define some pressure loads. Pressure load is going to go in the global Z direction, and I'll say that it's going to have a magnitude of 8.7 kPa, or kilonewtons per meter squared. And I'll just apply this to the entire slab. And you can see that for each shell, it's added an 8.7 kilonewton per meter squared pressure load, but it's ignored the areas where I have my hole panels. So that will be my dead load. I'm running an analysis right now just with that dead load. I'm just going to run it a linear static analysis just for this one load case. And while that's running, let's move on with the slides here. Because we want to get a better understanding for our result conventions. As you know, slab behavior is primarily out of plane. SRAM can easily calculate out of plane or even in plane forces, but we need to understand the conventions used for such results in order to actually use them. So just a few examples of some results that we might see. For instance, Fx acts on the x face in a direction parallel to the x-axis. So when I say x face, I mean this one here. And again, we can see parallel to the x-axis, the local z or x-axis rather of the shell. So it gives us an idea what that result is really representing. Mx is another result that we might see. And Mx is the moment on the same face. And this is also the moment resulting from spanning parallel to the x-axis. Another way that I like to think of this, especially since we're talking about slabs, is that any rebar parallel to the x-axis resists the loading mx. So imagine that we had rebar going in this direction, again parallel to the x-axis. That rebar would be resisting the force mx. And we can see here on this top right diagram how mx is represented. And we have multiple ways of interpolating contour results with SRAM, namely centroidal, nodal, and average. Let's go into a little bit of detail on each one of those. The centroidal option takes the average force on each shell surrounding the node, and this is where the values for the contour results come from, if you use that centroidal option. The nodal option averages the nodal forces of the shells attached to each node. And again, the results will not always be identical between centroidal and nodal. You can see there are two different ways of coming up with those results. And as you can probably guess by the name, the average interpolation option takes an average of the two methods that we just described, centroidal and nodal. And if you ever want more details on how these are come up with, you can always click on this help hyperlink here in the contour diagram factors dialog, and this will give you more details. And the defaults for number of contours, diagram styles, and so on are useful for most applications. And we'll stick with these standard settings in this example. If you look at things like number of contours, this can make the transition smoother between the different contour values. And the contour diagram style, really that's just a matter of preference. So you can change it to whatever you like. It's not going to change your results. I'm going to return to SRAM after I ran this analysis. You can see that we got a clean solution with no diagnostic messages. I'm just going to proceed on to the graphical results window now. And here, using the tools in SRAM, we can look at shell contour results. This is available when we have a mesh or finite element mesh. We can view this information as a contour diagram. So this is the FX contour. You can also view other contours. For instance, if I want to view, say, Z deflection, I can view those as well. So here I'm viewing the deflection in the global Z direction. We can see how it varies between 2.89 millimeters and negative 15.25 millimeters. And you can see based on the coloring where each one of those would occur. Now we can change this as well. We know we discussed the MX contour and what that means, the MX result rather. So let's look at the MX contour, and we can see here what sort of values we're dealing with. We'll just make a note of some of these values, and we're going to check for some convergence of these design moments. Note that if we're going to be using the design forces as opposed to the deflection, we should also check convergence of these also. So we want to check for deflection and moment convergence just to make sure that everything is converging on the mesh that we've chosen. So again, just to review, I had a deflection in the Z direction of 2.89 millimeters and a minimum of 15.285 millimeters, so that was a negative deflection. My moments, as we can see here, are ranging between 116.8 kilonewtons meter per meter and negative 36.5 kilonewtons meter per meter. Then we can check the convergence of the deflections by subdividing the mesh. So I actually have another model here that I'm going to open up with a finer mesh here. So here I just decided to open up this model with a finer mesh. We have about twice the mesh density that we did in the last example. We can look at the loading just to ensure that everything is the same. So to look here, we can see that we have 8.7 kilonewton per meter squared on each one of these shells. So the loading is identical. The only difference here is that we have finer mesh density. So we discretize this further. I'm going to go ahead and run this analysis. Just a linear static analysis again. And the reason I want to do this is I want to compare the results between these two models to see if I get any differences. Again, we're comparing two different results, one where we have a much higher mesh density than the other. So let's look at our contour results again. And I'll start off just by looking at the dz values, z deflection. And you can see here we're getting a maximum positive z deflection of 3 millimeters compared to 2.89 millimeters in the last example. And our minimum is negative 15.75 millimeters. And that's compared to negative 15.25 before. And we can also look at the MX contours because we don't want to just compare one, we want to compare multiple results to make sure everything's converging. And here we can see that for this finer mesh model, we're getting a maximum value moment for 155.8 kilonewton meters per meter. Compare that to 116.8. And the minimum is negative 38.2. And compare that to negative 36.5. So we do notice some differences here. One of the major ones being that spike in the positive moment. And again, before we made this webinar, I ran an analysis ahead of time, with other load cases as well. And we look at the MX contours and our deflection contours, we can see a range of value in each. We can use the analysis results from the different mesh densities to check for convergence of our results with different element sizes. So it looks like, it doesn't look like our MX results did actually converge when we were at that level going between our original mesh density and our finer mesh density. So that tells us really that our mesh density wasn't fine enough with this coarse mesh model because it didn't represent that peak moment. Perhaps it's maybe not even fine enough yet. We really would have to further discretize this mesh to get a good understanding of that. Now when we increase the mesh density to a certain point, we'll notice that the results essentially converge, except perhaps maybe right over the column where this is a singularity. Now to more accurately find out what's happening over the column, in the column head, we can take one of several approaches. One, we would be able to model the column using, or the column head rather, using stiff members to accurately represent the top of the column. Because right now we have artificially high stress contours at that point, where we just have a single member meeting the slab at just one single joint. In reality, there's no way that you would have one joint connecting to your mesh. Because again, your column, in this case here, our columns are 300 millimeters by 300 millimeters. So we would have a wider surface area to distribute that load. But now we'll look at why we might want to create a strip integration line to enable us to more accurately test for convergence over a specific point that may be of interest. For instance, it's column heads. It's a useful tool to integrate contour results at specific locations. And strip integration lines, they add no mass or any stiffness to our structure, so they're really just for post-processing, and they're very easily defined. Another advantage here is that, as you'll see later on, we can actually use these strip integration lines for design purposes when we're working with the integrated concrete design. And I'll show you just a quick example of that. So let's first look at the first type of strip integration lines that we have, the strip integration lines on the fly. This can be done actually by clicking the points that we'd like to integrate between. So here you can see I define my 1, 2, and 3 mouse clicks. So starting off here in a contour design result, I just click on a joint in my mesh, a second joint to define that strip integration line, and a third joint to define the orientation of my strip integration line's local coordinate system. And that gives me the results that I'm looking for in between there. And we can increase the number of strip integration points, the width of the strip, and even more with this on-the-fly tool. I'm going to go back into SRAM and actually go back to that original model I was working on with the coarser mesh, just because I personally prefer it a little bit easier to work with when we don't have quite as fine of a mesh density. But what I'm going to do actually is I'm going to delete all my existing shells that were created during the meshing operation. So I'm just going to select the shell tool and hold down Control to select them. I'll delete the triangular ones as well. And then using the joint tool, I'm holding down Control and I'm going to delete any nodes that aren't connected to existing objects. And I want to create a strip integration line basically just centered over top of this, this column header here, because I know that's going to be a point of interest. I have that column holding up my slab. There's going to be a lot of stress concentrations there. So the first thing I want to do to make this easier for me is I'm going to move my coordinate system to the top of this column and then create a grid. And I'm going to say that I'm going to have a strip integration line that extends 2 meters on either side of this column header. I use the member type tool here, and I'll switch it to strip integration line. If we want, we can define a strip width. I'm not going to worry about that for now. But now I'm going to go ahead and define member definition tool, and to define this strip integration line, you can see here it's defined. We don't need to define any dummy member properties because it's not going to have any stiffness or any mass, just based on this member type. It's not like a beam or a truss or anything like that. This has no stiffness or mass once we define it as a strip integration. So here I've gone ahead and I've created that strip integration line. Again, it's just a fictitious member that was only used for post-processing. And I've defined that on top of my column, centered over that column, 2 meters on each side. Now something else that I can do is I can go into the section properties tool and I can create a concrete section for that particular strip integration line. So if I wanted to here, I could go ahead and I could create a concrete section. I'll just remove some of my reinforcement to make it more like a slab contour, or a slab section rather. And we can just kind of guess the approximate properties that we want to use, but I know that's going to be 300 millimeters thick, same thickness as my slab. And then we can use this for integrated concrete designs, co-checking and design of this slab. We can always, just like as concrete, add additional bars if we'd like to. And I'll just give this a name, concrete slab section. And add this as a new section. And I'm just going to apply this just to my strip integration line. And I'll also make sure that the strip integration line has concrete material. Now let's go ahead and remesh this model. It's asking me if I'm satisfied with the mesh, which I have no problems with, so click yes. And we'll reanalyze this. And now we can look at our results. So one thing that we'll see here when we're working with contours, if I show you, for instance, the MX contours, I should have actually reapplied my loads as well. So let me do that really quickly here. Because I removed my shells, those shells had loads applied to them, and those were lost when I removed my shells. But now if I look at my results once again, here I'll just look at the slab contours for MX in this case. We can see that there's obviously a peak around this column header, but it's hard to really understand it unless we have a strip integration line there. So I can look at my strip beam integration line, change the number of stations, and I can get a much better understanding for the results in that one location. And we can see here that we're getting about 190 kilonewtons meters per meter of moment MX over this column. Now I went ahead and I also ran the analysis beforehand just to show you guys this in slides, just to save a little bit of time. So using the strip integration line here, we can see that the convergence is around 1% for the wood armor MX, which is satisfactory. Compare this to the convergence in the mesh, where we doubled the mesh density. So a twofold increase in mesh density yields only a 1% difference in wood armor moments. This is a good indication of convergence, at least in the moment results, and it would be very difficult to spot this without strip integration lines. As you remember, when we're just looking at the contours, it was harder to really understand the convergence of results. The strip integration lines are also useful for calculating the steel areas by creating a section of grids of strip integration lines. This is similar to how the codes work by defining regular grids. Now, contouring and strip results are all dependent on mesh densities, the model sophistication, and the methods used to calculate or average out the analytical peaks. Now, these capabilities and more are covered in more detail in our online training course F201. But as you can see here, it's good at identifying singularity. Because we had that one joint coming up into our mesh, it was much better at representing the effect of that than it would be if we were just using slab design contours. So some points to take into account. And now that we've verified the forces and the deflections in the model, we can look at designing according to the code defined required steel areas. There's some points to make or to take into account when designing slabs in SRAM. Steel requirements will align with principal stress directions. Torsion is accounted for in irregularly shaped slabs with SRAM's FEA solver. And this is accounted for using wood armor calculations in SRAM. Now, these wood armor moments are then used to determine steel area requirements. And SRAM only calculates flexural steel requirements, not shear. Now here we can see that we're showing the rebar thickness, the thickness of our slab, and the strain diagram, the stress force diagram. So SRAM knows the depth of the rebar, the thickness of the slab, and it creates a stress strain diagram. There's more information on this in the help system. But again, we have a lot of control over the diagrams that we're getting out of this too. For instance, the steel areas that we can calculate are based on various design codes, as well as material properties, and the rebar depth that we can define all within this actual dialog here. And they have the exact same settings available for us within the strip integration line results and the slab design contours that we'll look at later. Now I'm in the same course mesh model that I was working on before, in the graphical results window, and I'm going to open up the slab design dialog here. This is the slab design contours. I'm going to right click on this to open up the slab design dialog. Here we can choose which concrete design code we want to use. For this particular case, I'll set it to ACI 2011. Then we can set the X direction and Y direction, top and bottom rebar here. I'm just going to stick with the 80% effective depth. And once we're satisfied with that, we can click OK. Now we can do things like show the contours, not only for MX, in this case MX top wood armor and bottom wood armor, but we can also show things like X steel top, for instance, X steel bottom. So this is showing us the rebar requirements for flexural resistance in this location. I'm going to reopen this slab design dialog. And here we'll say, again, if we look at this user-defined minimum and maximum ranges, which is available by adjusting this contour magnification option, we can scroll down here and we can see that we can set minimum and maximum values for each one of these contour results. So that what that helps with is that if we exceed that minimum or the maximum or a minimum value, we can set specific colors to let us know if that value has been exceeded in a specific range. And where that's useful is for our steel reinforcement requirements. So we'll say that we're applying a consistent 800 millimeter per meter squared mesh of steel reinforcement in the X direction at the top of the slab. And if that value is exceeded at any point, we'll have this value or this color show up in the contour. I've deliberately set this to be a very distinct color so that I can pick it out from the rest of the colors. So we can click OK now, and we can see here that around these column headers we're getting that value exceeded. We can also look again, before I showed you guys the X steel bottom, we can see the same contour results. Now this particular case we have a different range for our top and bottom bounds. And we can see that it's only being exceeded by the looks of it in this one location here on the corner of this whole panel. And we can make the contours in SRAM work for us. SRAM can calculate and display our steel reinforcement demands. We set up the diagrams, the diagram displays to highlight potential areas of concern like we saw just in that last example. And with the ability to customize our display and the display of our results, we can have SRAM show us only what we need to see. This is useful when sharing results with clients who may only be concerned with certain information. It gives us a lot of flexibility over the information that we show. Now, some pointers to consider when designing slabs and finite elements. There may be a need to amplify the amplify the magnitudes of sagging moments in the presence of pattern loading. And this can be done through multiple load cases or combinations with load case factors. You can also estimate long-term cracked section properties by adjusting the stiffness of your material. And we have clients who trust SRAM for the slab design for its ease of use. You saw its efficiency. We were looking at a whole structure. We looked at the entire structure all at once, rather, and for its accuracy. Now, there's a couple of ways that we can look at improving our model as well. If we needed to add line loads to represent perhaps wall forces from a non-structural wall on our slab, we could do that by adding line loads. There's a few different methods of doing this. We could add a truss member. That truss member, we'd try to give it as little stiffness as possible by giving it very small section properties. We could also add an integration line then to the mesh to ensure compatibility. You can see here the mesh is connected to that line. And we could add a line load to that integration line as well. And we talked about column headers before, and we can use dummy members to accurately model the column head to the slab as well. So as you see here in this particular model, where we have our strip integration line crossing the top of that column header, again, before we just had that one joint connecting to our slab, to the slab's mesh. So we had that artificially high concentration where the column connects to that slab only at that single joint. We could actually define rigid links to transfer those loads to the outside and get a better understanding of how the column header would actually interact with the slab in real life. So this would help reduce those singularities that we saw, like in that last example, again, where we just have that one column pinning up essentially into our slab. So it would be like a pin connected to our column, where it's just very tiny, just all the force is so focused on one location. Now all that information that we've found, it's really no good to us if it's just locked within SRAM. So we have to be able to report that to the outside world as well. So we have spreadsheets that we can output. We can export these spreadsheets to Excel, for instance. We can export these images that we see to Word documents and control exactly what we want to export. And all the formats are defined by you. So for instance, we have PDF reports, or PDF4 reports, sorry. We have Excel and CSV files as well for any post-processing purposes. And if you use the integrated concrete design, like I'll show you in just a second, we can get a lot of reports right out of that integrated concrete design, for not only for our slabs, but any other concrete objects that we have, any beams or walls or columns. So I just want to show you that really quickly here. Again, I have that concrete slab strip integration line that I just defined just for the sake of demonstration. And here we're showing the X-scale bottom here for the strip integration line. But again, I gave it concrete slab a section property. I'll just review that. This concrete slab section here, I went into concrete and just defined this section property for that slab. So it's going to take all the results from that strip integration line and use that to design that slab section. So I'm going to click on the Build Concrete Design model. And it's brought me into the integrated concrete design. I can select that particular member, in this case it's a strip integration line member, to represent the slab section. And I can run a code check on this slab. I'll just run it for the dead load case. And we're able to get results for this slab. Again, this is just looking at the results for the strip integration line. And as you may remember, I do have some singularity along that line. I'll just show you here really quickly. You can see that the shear and torsion utilization is failing, as well as the axial force and moment. So that's likely due to the fact that we are looking at this slab strip essentially right over top of that column header. If we were to model our column headers with those rigid links, like I described in the slides, we'd probably actually be able to distribute this force a little bit more evenly, so it wouldn't all be popping up just at the top of that column. So we introduced you to the topic of slab design today in SRAM. And using SRAM, we defined a finite element model of our slab and looked at ways that we could refine it. We obtained analysis results from our model and used those results to determine the flexural steel requirements. That information is of little use to us, however, unless it can be shared with others who may not have use of SRAM. That's why SRAM comes with a host of reporting options so that the information you obtain isn't stuck in the software. Now, our users prefer SRAM for slab design because it's easy to use, it's efficient, and it's accurate. So hopefully you guys were able to get an appreciation of that today. There's a question on how to define rigid links between the column and the slab. So this can be done a number of ways, but what we recommend, if we just go back to that slide for a second, here is that you can define rigid links. These rigid links would likely be members that are very stiff, so they have a large section property, and perhaps they don't have any material density because you don't want to double count your mass in that section. You just want to basically distribute these forces to the joints that would be on the perimeter of your slab, or your column, sorry. Now there's a question asking about meshing in general. So I won't go into too much detail because there's obviously a lot that we could discuss when it comes to meshing. But they're asking if a higher density mesh will come up with a higher result for your moments. It really depends on the situation. It depends if you have a spike in your mesh that may be missed if you have a coarse mesh. Or sorry, a spike in your results like a column header that might be missed if you have coarse mesh. A finer mesh is going to do a better job of representing that. As you can see as well, those strip integration lines also do a good job of integrating those results exactly over top of that location. So strip integration lines and wall integration lines, which we didn't look at today, are really good for that sort of post-processing. And the last question we'll cover today, again because we are running short on time, there was a question again on why we chose to use uniform pressure loads over area loads. Well, area loads, they behave a little bit differently. Area loads in SRAM distribute the results, or sorry, the loads that are applied to a panel to area load members. So they distribute them to members rather than to a finite element mesh.